Greetings everyone, and welcome to another online Kinematics and Dynamics of Machine lecture. Today we're going to be covering section 2.3 in chapter 2 of Wilson and Sadler's Kinematics and Dynamics of Machines. This is applying analytical vector methods in order to determine the displacement or the position of various mechanisms. Please note that you should take a look through sections 2.1 and 2.2 if you haven't already done so, and you should definitely read through section 2.3 in the book as background to the lecture. Note too that we have quite a number of homework problems that are here for you to practice these methods with. I will be posting answers to these, not solutions to all of them, but definitely answers, so that you can verify your solutions. And of course, as always, I'm available during office hours to review any problems that you may have. So let's get to it. But let's first start with just reiterating one of the most important things in any engineering problem solving. The first rule is don't panic. Panic never really helps solving any problem. The second rule is start with something easy. So along those lines, doing a sketch of whatever kind of problem we're trying to solve is always appropriate. We'll see how that applies momentarily. So, for any of the linkages that we've looked at, we've drawn just stick figures diagrams showing rigid links between joints and then applying nomenclature to it so that we're consistent. But we can also define these links, instead of just as lines, as vectors, and therefore create a closed vector chain from them. Let's see what that looks like if we draw it. So, let's start by drawing, I don't want that. Start by drawing our fixed link. As you can see, I've defined a vector. A vector has a magnitude and a direction. So in this case, I've defined my fixed link as going from point 0,3 to point 0,1. If I continue along with that, I can draw my L sub 1, or crank in this case for a 4-bar link, L sub 2, and L sub 3. Let's go ahead and label these. So we can see by drawing upon the vector lecture that we had last time, if we physically add these vectors together, L sub 0, L sub 1, L sub 2, and L sub 3, we get back to where we started. We've created a closed vector chain. That's what this equation represents. Now, for any planar vector equation, we can go ahead and make a general definition that adding A plus B plus C is equal to 0 if they are a closed vector chain. If C is an unknown vector, and we decompose vectors A and B, we can reorganize that equation to say that C is equal to the negative sum of the x components of A and B multiplied by the unit vector I minus the sum of the y components of A and B multiplied by the unit vector J. Or we can reorganize it a little bit further using that interpretation that the dot product of a vector and a unit vector is the projection of that first vector in the direction of the second. So this allows us to do something kind of interesting. The next few slides are going to be very important, so you should definitely highlight them in your printout of the notes, assuming you make a printout, or at least make note that these are very important in whatever other notes you're taking. So, in the first case, if the magnitudes of two of these vectors in whatever system we're looking at are unknown, just the magnitudes, but if we know the directions, we can use that a plus b plus c equation to generate this result. If we then solve for each of the unknown magnitudes, in this case a and b, we can find these two equations to generate the magnitudes. So again, going back to our single degree of freedom concept, if we know the magnitude of one of these vectors, in this case c, then we can use that to find the magnitudes of a and b. The derivation of these equations is on page 118. It's a little bit tedious, so I'm not going to take you through it, but please do kind of glance through it just so you can get a feel for what's going on. The next possibility is if we know all of the vector magnitudes, but not the directions of two of these vectors, then we can again manipulate those equations to come up with some fairly long, fairly involved equations that give us the directions of vector A and B. Because of the derivation and the way things are defined, if our vector loop is clockwise, we use the lower sets of signs in these equations. So just to make sure we know what we mean by the vector loop being clockwise, run back to this. This is a clockwise vector loop. If I start from any given point and follow along the directions of these vectors, you can see I'm going clockwise. That's clockwise. If we were going the other way, then we would use the other set of signs. Okay, so continuing on, we had the first setup where we knew the directions but not the magnitudes. Now we have this second set of equations that if we know the magnitudes, we can find the directions. The third set is if we know the magnitude of one of the vectors and the direction of the other, or contrariwise, if we don't know the magnitude of one and don't know the direction of the other, we can use these equations to solve for what we don't know. So, next up, we will see how to do this. It's going to be a second portion of this video. I'm not sure if I'll stitch them together or post them separately, so just hold on a second. We'll see how that goes. Okay, guys. We're going to see if we can't go through sample problem 2.4. This is on page 119 in your book. And it illustrates one of these vector analysis problems. What we have is a slider crank. Let me read the problem to you. Suppose an inline slider crank, and I'll draw the figure in a moment, has a crank described by the vector r sub 1 equals I plus j2, and a connecting rod length r2 is equal to 4. Find the connecting rod orientation and the slider position. So, we have a system that kind of looks like this. So, it's a slider crank, O1, B, and C. Our normal definition for something like this, we will define the center of the crank as the origin, and therefore we have a nice XY coordinate system. We're told that r sub 1 is equal to I plus 2j, and r sub 2 is equal to 4, and we want to find r sub 2 u, its direction, and r sub 0. So, a couple of things we should probably mention immediately, a couple of things that are worth discussing. We always want to start by not panicking, and then we want to do something easy. So doing something easy in this case can consist of drawing our system, and also maybe of playing around a little bit. R sub 1 is equal to I plus 2j. What does this mean? Well, it means that R sub 1, I didn't draw it terribly well in my initial figure, but that doesn't matter, kind of goes like this. So it has a height of 2, that's along the j-axis, and a run along the x-axis of 1. So just by trigonometry we can figure out this angle. It might make us feel better to do so. I'm afraid you probably won't be able to see my calculator screen, but nevertheless what we would do is say opposite over adjacent is equal to the tangent of this angle. Therefore, 2, the inverse tangent, tells me that this angle is 63.4 degrees. Now I feel better. I've done something easy and simple, and that gives me some more system feeling. I can also go ahead and identify these links as vectors. I said that this was R sub 1. I'm going to define a closed vector chain that is going clockwise. R sub 2 then is the conrod, and R sub 0 is the position of the piston from our origin. Now we should note a couple of things from this sketch too. Even though it's not terribly dimensionally correct, it can tell us something. We know that R sub 1 is positive I, positive j, so it's definitely going up and to the right in our coordinate system. R sub 2, since it's going down and to the right, this should be positive I and negative j when we get its answer. And R sub 0, which is horizontal, nice benefit of defining the problem this way, should only have a negative I component. Now if I go back and take a look at slide 7 of the notes, I can find that this system corresponds to what's mentioned in slide 7. Specifically, that we know the position and orientation, so the direction and magnitude of one of the vectors and the length of the other. Now, with this kind of setup, we can recognize that this is a 3-vector setup, so it kind of corresponds to the A, B, and C in your notes in the book. In these cases, C corresponds to this side, the one that we know. These other two are A and B. So I can use the equations on slide 7 to write the following. I can say that R sub 0 is equal to negative R sub 1 times the unit vector of R sub 0 minus plus R sub 2 squared minus R sub 1 R sub 0 unit cross K square that. This entire portion of the equation we take the square root of, and this whole component is multiplied by the unit vector for r sub 0. So, looks fairly complex, but it's not really that bad. We can start by saying r sub 0 u from our definition of the system is equal to negative I. We can also go through and start selecting portions of this to solve as little chunks. So why don't we do that? The cross product of r sub 0 u and the unit vector k, so k is coming out of the sheet. If I take that cross product, r sub 0 u and k, it's going to cross like this. So by the right-hand rule, this is equal to the unit vector j. So remember, we're going tail to tail. R sub u is negative in the x-axis. K is coming up. I cross r sub u into k, and I get something that's j. Sorry, just hit the camera. Hope that didn't make anybody seasick. So let's see here. That gives us this portion. Now I can say that r sub 1 dot product with j now let's see here. R sub 1, we're trying to get its magnitude, because remember that the dot product is equal to the magnitudes of the two vectors multiplied by the cosine, the angle between them. So this magnitude would be 1 squared plus 2 squared square root, so the square root of 5. So this can be the square root of 5 for the magnitude of r sub 1 multiplied by 1 for the magnitude of the unit vector j. Now the angle between them, fortunately we figured out that the angle of r sub 1 with the horizontal is 63.4. So the angle back to j should just be the 90 degrees minus 63.4. So it's be equal to the cosine of 90 degrees minus 63.4 degrees. And if I run through that calculation, I get that this is equal to 1.999. We'll just call it 2. Let's see, what else can we do? So now we've solved this. The remainder inside our square root is r sub 2 magnitude squared minus what we just figured out squared. So r sub 2 magnitude squared is equal to 16, and 2 squared is equal to 4. So that whole portion, it's just going to confuse things, 16 minus 4 square root, so that's the square root of 12, so about equal to 3.46. Alright, so now we've figured out this whole thing. Now we are doing this as a clockwise, so we're going to use the lower sign. Therefore, we've got still this negative R1 dot R0. So going with what we had before, negative square root of 5 times 1, the angle between R1 and R0, we already know it's 63.4 degrees. So if I do this, this comes out to be about equal to negative 1. Okay, so this gives me all of the things in here. I'm going to end up with an equation that says R sub 0 is equal to negative 1 minus or plus 3.46. And this is going to be multiplied by our unit vector for R sub 0, which is negative I. So we are using the lower. That says we should be, let's see, negative 4.46 I. So there's R sub 0. So far, so good. Second equation looks like this. And again, just substituting things into the equations in the notes. I'm not repeating all of these as I write them down, just so you don't get too bored of hearing me speak. Whew. Long equation, but not maybe as scary as it looks, because we've already figured out what this is, and the rest of it should hold no real worries either. If you work through this, what you'll find is that RU cross K is the same thing we had before. So this is just J. R1.J ends up being 2. We already have that. So this very quickly gets us down to that R2 unit vector being equal to negative 2J plus or minus negative 3.46I, or if we convert that into a more common type of notation, 3.46I minus 2J. So you'll note that these directions do match what we had said before from our sketch. R sub 2 should have a positive I and a negative J. R sub 0 should be a negative I. We can verify that this is correct by checking against this equation. r sub 0 plus r sub 1 plus r sub 2 is equal to 0. I'll leave that to you guys to double check, but this is the base equation that we run with. If we create a closed vector loop, then whatever vectors we generate should satisfy this equation. Hopefully that wasn't too confusing. We will run excuse me, through a couple of more sample problems on Wednesday, but this is the kind of thing that you should expect to see on exam 1. Alright, thanks very much. Hopefully, again, this wasn't too boring, and I'll look forward to seeing you guys on Wednesday. Stay safe and stay warm.